Okay, I'll get started. Just wanted to begin, of course, with the reminder that test 3 is in exam week. It's on the Thursday at 8 a.m. in here. Test 3 has exactly the same format as test 1 and test 2 with the true-false questions and the 3 long problems and the same equation sheet. Test 3 is covering all that material that we've covered since test 2, so it's covering the material where we explored the properties of light, it's covering the material where we use light to expose the properties of space and time, relativity. It's covering the material where we've also used light to expose the properties of subatomic particles, or are exposing the properties of subatomic particles in these last few classes. Any questions on all that? The other reminder is, in case you haven't already done so, to complete the teacher-instructor course evaluation. I really appreciate that. That's very useful. Once we get to 80% completion, I'll credit everybody for a 1% bonus for the TCE completion. Any questions on that? Then I'll move on with today's material. Last class we talked about wave and particle properties of light, and in today's class we're going to talk similarly about particle and wave properties of matter. So that's the basic content. Most specifically is to introduce what we call matter waves, introduce the concept of matter waves. So I'm going to walk through these 3 bullets on this slide. I'm going to introduce the idea of matter waves and the wave-particle nature of matter. I'm going to remind us of the particle properties of light and the wave-particle properties of light. And we'll see that we've kind of synthesized, joined together our pictures of light and our pictures of matter by introducing wave and particle properties for both light and matter. And so we have a unified picture of light and matter, which is a big breakthrough. Second bullet here is really hard to read. I want to at least show you how matter waves the existence of matter waves was proved, was observed, was experimentally verified. So we'll look at the experimental proof verification of existence of matter waves. And then finally, wave-particle duality, the existence of matter waves, has a huge implication for our understanding of the nature of the universe. It was really a kind of tipping point from what was a kind of clockwork, classical, universal, to a more probabilistic, undeterministic universe in modern physics. And so we'll discuss that. And we'll discuss a quantity called a concept called the uncertainty principle, which kind of codifies or embodies this probabilistic, undeterministic nature of the universe. So this is the plan. Okay, so let's start with the idea of matter waves and the synthesis, joining together of light and matter. That's going to be our first topic here. This is the classical description of matter and light. This is the starting point for our description of light and matter. In the classical description of light and matter, well, I've got light over here on the right-hand side, and I've got matter over here on the left-hand side. For matter, classically, we think of matter as little particles, little bodies, little objects. Those particles carry energy and momentum. And so that's our picture of matter, little particles with energy and momentum. Our classical picture of light, well, our light is something that is a smooth and diffuse wave with wavelengths and with frequencies that reflect the distance between crests of the waves, or the time between successive crests of the waves. So that's our picture of light classically. And this was the situation at the end of the 19th century, end of 1800s, the beginning of the 20th century. That there were two sort of types of media in our world. There were waves, light is the classic example, and then there were particles like, for example, electrons or atoms, and they had very distinct properties. What emerged as science progressed from the end of the 19th century into the beginnings of the 20th century was a realization that actually light has particle-like properties, doesn't always look like a wave, and that matter has wave-like properties. It doesn't always look like a particle. So that was a huge breakthrough, and that was a split in our understanding of light and matter from a classical picture to what we would call a quantum picture, or a modern picture of light and matter. So on this slide here, I've again got light on the right-hand side, and I've got matter on the left-hand side, like this last slide. But this is not classical light, classical matter. This is modern light and matter, quantum light and matter. So for light, we understood in the last class that light also exhibits particle-like properties. It's kind of absorbed and emitted and interacts as particles. Those particles own energy and momentum, like classical particles do. So it exhibits particle-like properties. And then over here on the left-hand side, the new thing is that matter not just has particle-like properties, it has kind of a fuzziness or a diffuseness to it. Electrons or atoms or molecules have a fuzziness, diffuseness to them that reflects the matter wave-like properties of matter, and they exhibit a wavelength. So they exhibit waves with crests and troughs, and a separation, a wavelength between the crests. They exhibit a frequency. They exhibit, again, waves that oscillate in time with an interval between successive crests. And so matter exhibits wave-like properties too. So this really represents, now if we look in light and matter on the left-hand side and the right-hand side, they both own wave-like and particle-like properties. In that sense, they're described in a more complicated way because they have wave-like and particle-like properties. On the other hand, they're described in a unified, a synthesized way because they both exhibit wave-like and particle-like properties. So the important point here is that light, for example, is no longer simply a wave. We can no longer imagine light as simply like an ocean wave or a sound wave from our everyday world. And particles are no longer simply little particles, little billiard balls. We can no longer imagine them like that from our everyday world. Particles and lights, electrons, say, and photons, they exhibit particle-like and wave-like properties. They are really neither particles nor waves. So light and matter are neither particles or waves. Rather, they're something that we have no no experience of in our everyday world, because our everyday world is all about things that are either particles or waves. They are something that we don't have any of that experience of in our everyday world. They are something that exhibits both wave and particle-like properties. There's some sort of entity that's in a way more complex, more difficult to imagine, that has wave and particle-like properties. I don't know what to call it. None of us know what to call it. I mean, you could call it a wavicle or something like that. It's just some entity, something that exhibits both particle and wave-like properties, and they both exhibit that nature, wave and particle-like properties. And there's nothing in our everyday experience, nothing in our everyday world that allows us to imagine what a particle like an electron is, or what a photon of light is, because we don't have any experience in our everyday world of things that exhibit particle and wave-like properties. So that makes it tough. Planck's constant, we introduced Planck's constant a class or two ago. Planck's constant sets the scale of the transition from our kind of everyday world where something is a wave or something is a particle, to this strange quantum world where things have both wave and particle-like characteristics. So Planck's constant is a constant of nature that sets the scale of the wave-particle world and differentiates it from the I'm a particle or you're a wave world of our everyday experience. So Planck's constant really sets the scale of light's granularity and matter's fuzziness, waviness. If we were able to do this, right, supposing you could go into nature and we could change Planck's constant. Planck's constant is about 6 times 10 to the minus 34 joules seconds. That's roughly what it is. It's about 10 to the minus 15 electron volts seconds. That's the value it is in nature. But supposing I could go in and change it, and supposing I could turn it down and down and down, make it smaller and smaller and smaller, and make it 0. If I made Planck's constant 0, then light, electrons, light would be simply a wave, and electrons would be simply particles. We'd have our everyday experience of light and electrons, of particles and waves. So turning off Planck's constant effectively reverts us to a world of classical physics. It reverts us to a world of everyday experience. It reverts us to a world where things are particles or they're waves. They can't exhibit particle and wave-like properties. If we were to turn up Planck's constant, I said it was about 6 times 10 to the minus 34 joules seconds, very small number in those units, about 10 to the minus 15 electron volts seconds, also a small number in those units too. But if I turned it up, supposing I turned it up to 6 joules seconds, well then we'd be living in a world where everything exhibits particle and wave-like properties. You would exhibit both particle and wave-like properties. I would exhibit particle and wave-like properties. So you would exhibit particle and wave-like properties in that you could transfer energy and momentum to and fro when forces acted on you, or you exerted forces on something. But you would exhibit wave-like properties because you would interfere with the person next to you, in the sense that waves interfering. And likewise for me, I could transfer energy and momentum just like a particle, but I could interfere just like a wave with things around me. And so if Planck's constant was 6, not 6 times 10 to the minus 34 joules seconds, we'd live in a completely different world where we'd had everyday experience of the wave-particle nature of matter at its smallest scales. This is kind of a summary of wave-particle nature of matter on the left and light on the right. I've just added to the picture 2 equations, really. this one over here, this is a new equation, and this one over here, this is an equation from last class. These two equations, the one on the left and the one on the right, are like bridges. They're bridges between the wave and particle descriptions of light and the wave and particle descriptions of matter. So they connect, they join those two characteristics. So E equals HF, formula we met last class, that relates the wave properties of light through the F, which represents frequency, to the particle-like properties of light through the E, which represents the energy of a quantum of light. And in that relationship is Planck's constant, which is setting the scale of wave-particle duality. So E equals HF is the sort of poster child, I think of it, for wave-particle duality of light. The other equation, the new one, lambda equals h over p, that relates the wave and particle-like properties of matter. So it's the version for matter. It's called de Broglie's equation after a French scientist, also a French duke, who came up with the idea, who originated the idea of matter waves in analogy to the idea of light particles that Einstein and Planck had originated. So de Broglie tried to synthesize our understanding of light and matter by saying that, well, if light exhibits particle-like, wave-like properties, maybe matter exhibits particle-like, wave-like properties too. And he developed this equation, very simple equation, that lambda equals h over p, to bridge the gap between the space between the wave-like and the particle-like properties of matter. So in this equation here, that new equation, P is the momentum of a particle. Maybe it's an electron, maybe it's a proton, or maybe it's an atom, a molecule. It's the momentum of that subatomic particle. And lambda is the corresponding wavelength of its matter waves, the electron matter waves, the proton matter waves, the atom or molecule matter waves. So this is the bridge between the wave-like and the particle-like properties of matter. And again, in that equation, there's going to be Planck's constant, because Planck's constant sets the scale of sort of wave-particle duality, this strange nature of matter and light at subatomic scales. And so we see this equation here. So these are the two equations that bridge these worlds of waves and particles for light and matter. When you see these two equations, you might wonder, well, why are they different equations for light and matter? They're really actually not different equations for light and matter. You can turn the one on the left, lambda equals h over p, actually into the one on the right, just by a little bit of algebra, substituting equations. You can turn the one on the right for light, E equals hf, you can turn that into the one on the left. Again, just by a little bit of algebra, you can rearrange it. It's just history, practicality that led to these two equations being the posters for matter's wave-particle duality and light's wave-particle duality. But at their core, they're the same equations. You can turn one into the other using the equation that lambda f equals the speed of light. You would use that equation. And then you would use the equations that relate the energy and momentum of a particle like an electron, or the energy and momentum of a photon, a granule of light. But using those equations, you can turn one into the other. So they really are the same equations. It's just practicality, history. We represent wave-particle duality for matter and for light with these two different brands of the equation, versions of the equation. Okay, that was a huge step forward. Let me do this on the document camera. I just want to calculate use that de Broglie equation. So I got a couple of questions here actually, if it's readable. Calculate the de Broglie wavelength. Such a breakthrough. He owns that wavelength. It's the de Broglie wavelength of the de Broglie matter waves. Let's calculate that wavelength for two different objects, two different particles. One is going to be an everyday particle, a basketball. We'll calculate the de Broglie wavelength of that. The other one is going to be a subatomic particle, electron. We're going to calculate the wavelength of that. So let's go ahead and do that. I'll start with the basketball. So we want to know the part one here. We want to know the de Broglie wavelength of this basketball. Well, the de Broglie wavelength, lambda, equals Planck's constant divided by the particle's momentum. So first we need the momentum of the basketball that we're told has a mass of 0.6 kilograms and a speed of 10 meters per second. Well, the momentum of that particle is just mv. And so 0.6 kilograms times 10 meters per second, I can do that in my head. That's 6, 0.6 times 10 is 0.6, and its units are kilograms meters per second. So that's the momentum of the basketball. And then if I want the wavelength of the particle, I just got to take Planck's constant and divide it by that momentum. So Planck's constant is 6.6 times 10 to the minus 34 kilograms, joules seconds, divided by my 6 kilograms meters per second. The number there, well, look, that's 6.6 over 6, so it's going to be, the number is going to be 1.1. 1.1 times 10 to the minus 34. And the units, we got a little bit of a mess of units. We got joules seconds over kilograms meters per second, but that simplifies actually down to just meters. And wavelength is a distance, so it is in meters. And so that's the de Broglie wavelength, the matter wave wavelength of a basketball. You see that it's absolutely tiny. Think of the size of a basketball, this big-ish. 10 to the minus 34 meters is nothing, absolutely infinitesimal compared to the scale of that basketball. So yes, the basketball does exhibit matter waves, but no, they're not relevant to playing basketball because they're so absolutely tiny. That's why we don't notice matter waves, interference of matter waves, effects of matter waves in our everyday experience, because the matter wave wavelengths are so absolutely tiny. It's a little different for the electron. Let's calculate the same thing for the electron. We want to calculate the momentum first for the electron. We know its speed. Then we can, once we got the momentum of the electron, we can calculate its de Broglie wavelength. We can see what that is. So the momentum of the electron, this electron, we have to be a little bit careful here. Its speed is 1,000,000 meters per second, so it's going fast. So we might think about relativity, but actually 1,000,000 meters per second compared to what's the speed of light? 300 million meters per second. It's going very fast compared to the basketball, but it's much slower than the speed of light, 300 times slower than the speed of light. So I'm just going to use mv. But if it were going faster, if it was going the scale of the speed of light, I would want to use gamma mv here, the relativistic momentum. But I'm just going to use mv. The mass of an electron, I've got to look it up here, sorry, because I think it's 9.1 times 10, yeah, 10 to the minus 31. That's the mass of the electron. The speed of the electron is 10 to the 6 meters per second. So I can do this calculation in my head too. It's going to be 9.1, because 1 times 9.1. We got minus 31, power of minus 31, and a power of 6 here. And so this is going to be times 10 to the minus 25. And this is kilograms meters per second. So that's the momentum of our electron. And if we want the wavelength of our electron, its matter waves, then we've just got to divide Planck's constant by that momentum. And so I'm going to start to panic with time, so I'm not going to write in all the numbers, but it's 6.6 times 10 to the minus 34 joules seconds divided by 9 times 10 to the minus 25. It's kilograms meters per second, and that comes out again to be a distance, a number of meters, a wavelength, and I wrote down the answer is 7 times 10 to the minus 10. 7.3 times 10 to the minus 10 meters. That's a small number, 10 to the minus 10 meters, but it's nothing like as small as 10 to the minus 34 meters for the basketball. It's nothing like as small because it's much, much bigger than the wavelength of the basketball, because the momentum was much, much smaller than the wavelength of the basketball, and the momentum goes in the denominator of the calculation of the wavelength. So the bigger much smaller momentum of the electron compared to the basketball led to a much larger wavelength of the electron compared to the basketball. Now this is interesting. 10 to the minus 10 seems small compared to everyday distances, but 10 to the minus 10 is not small compared to the size of atoms and molecules and things like that at the subatomic level. So this is telling us that at the subatomic level, the fact that electrons have wave and particle-like properties is going to be important, because their wavelengths are the scale of the sizes of atoms and molecules, and so their wave properties are going to be important at the scale of sizes of atoms and molecules. So that's a big breakthrough. Okay. So just to conclude that section with a comment, I want to stress that, I never changed back. I just want to stress this little statement I made here. What we've discovered is that electrons, or it could be protons, or it could be atoms or molecules, but subatomic particles sometimes behave like particles as if they're particles, and sometimes they behave as if they're waves. The same would be true for photons, or light, or infrared, or ultraviolet, or X-rays, or gamma rays. Right? They sometimes behave as if they're particles. They sometimes behave as if they are waves. Now, I'm being a little bit careful. Okay. Firstly, I use this word sometimes. I use the word sometimes behave as particles and sometimes behave as waves, because you never see an electron or you never see a photon behave simultaneously as both a wave and a particle. It either behaves as a wave or it behaves as a particle. An electron or a photon either behaves as a wave, or you observe it behaving as a particle. So that's one point. Also, I say as if it were a particle, or as if it were a wave. The electron behaves as if a particle or a wave. The photon behaves as if a particle or wave. I'm saying as if because an electron is actually neither a wave nor a particle. A photon is neither a wave or a particle. An electron and a photon and other subatomic things are something, some entity that exhibits both wave and particle-like properties, but it's some more complicated, hard to visualize, hard to imagine entity that is actually not simply a wave and not simply a particle. Okay, I want to show you a couple of slides about how it was established, how it was proved, how it was observed that matter has wave-like properties. Say how electrons or protons or atoms or molecules have wave-like properties. Because it's fine for Duke de Broglie to come up with the idea, the conception of matter having wave-like properties, and fine for him to invent a little convenient, cozy formula for the wavelength of matter waves. But the question is really, do they exhibit these properties or do they not exhibit these wave-like properties? So when he invented his formula, he just invented his formula for the wavelength of particles like electrons and protons and so forth. But there was no evidence at that time. There's no evidence that particles have wave-like properties. I show the soap bubble here because one of our items of proof that light exhibits is a wave was reflection of a soap bubble. You might remember that. We said that when light reflects off a soap bubble, it reflects off the outer surface and the inner surface of the soap bubble. And the reflection off the outer and inner surface leads to interference of the light waves, and you get a colorful pattern of constructive, destructive interference in the surface of the soap bubble due to that interference. Well, the amazing thing is that this same trick to establish that light has wave-like properties was used to establish that electrons have wave-like properties. So exactly-ish, the same experiment was done, not for light of a soap bubble, but actually electrons of, not a soap bubble, a crystal. So I want to show you how that works. Okay, firstly, this is a step towards showing you that electrons have wave-like properties. This is a step that involves showing you that X-rays, a high-frequency light, has wave-like properties. So X-rays have wavelengths that are very short compared to visible light's wavelengths. Visible light's wavelengths are hundreds of nanometers long. So let's imagine here's 100 nanometers. This is the scale of visible light's wavelength. X-rays at the dentist, right? X-rays at the dentist, they have wavelengths that are nanometers in length, so 100 times smaller. So here's a visible light ray, this nice red light ray, very cozy. And then here's a little X-ray at the dentist, much, 100 times shorter wavelength. So how do you prove that X-rays have wave-like properties? We proved that visible light has wave-like properties by the soap bubble reflection. Well, you can do a, quote, soap bubble reflection for X-rays. You don't do it with a soap bubble that you just blew in your kitchen. You do it with a crystal. A crystal. A crystal is a regular arrangement, a regular array, a lattice array of atoms or ions. And here's a picture of the surface of a crystal. So this might be a sodium iodide crystal. Let's invent that this is a sodium iodide crystal, and the red dots here are the sodium ions, and the blue ones are the chlorine ions, and they're all lined up in a regular array. This is the top layer of the sodium iodide crystal. Beneath it is a second layer of sodium ions in red, chlorine ions in blue, all arranged again in a regular array down here. And your whole crystal is these regular arrays of ions. This looks a lot like the soap bubble. What I've drawn looks just like the soap bubble. That had an outer surface off which light was reflected, had a lower surface off which light was reflected. The two light sources, the bottom surface, the top surface, the inner and outer surfaces of the soap bubble cause the interference. Here I got the top layer of the sodium iodide crystal. I got the layer below it of the sodium iodide crystal. They're both going to scatter or refract the X-rays, and so we'll get interference of the X-rays. The thing about the soap bubble was that the thickness of the soap bubble was the scale of 100 nanometers. It's the scale of the wavelength of visible light, and so that's why it worked. The thing about the crystal is that the separation between the layers of the sodium chloride crystal, that's the scale of nanometers, which is the scale of X-rays wavelength of light. So scattering or reflecting X-rays off a sodium iodide crystal is just like scattering or reflecting visible light off a soap bubble. In both cases, I'm picturing a couple of layers from which the light or the X-rays are reflected. I'm understanding that if the light or the X-rays have wave-like properties, then you'll get interference from the scattering off the top and bottom surfaces of the soap bubble or the first and second layers of the sodium iodide crystal. And this was actually how it was proved, how it was established that X-rays also have wave-like properties by scattering off the layers of a crystal. This looks like the same slide, but now it's electrons being scattered or diffracted off a crystal. So now all I've done is replace the X-rays, which were scattered off the first two layers of the crystal and exhibited a interference pattern. I've replaced the X-rays with electrons directed at a crystal, and then I'm going to scatter those off the first two layers. If those electrons have wave-like properties, if they have wave-like characteristics, then there'll be electrons that are electron waves that are scattered off the top layer of the sodium iodide crystal here, electron waves that are scattered off the next layer of the electron crystal here, just like the X-rays were scattered off the top layer and the layer below it. And just like the X-rays interfered with one another because they have wave-like properties when they're scattered from the top and bottom layers, if the electrons have matter waves, then those matter waves will interfere with one another when they're scattered off the top and bottom layers of this sodium chloride crystal. And that's what was discovered. That if you replace the X-rays in your little experiment where you're scattering the X-rays off a little piece of sodium chloride, little salt crystal, with electrons, a beam of electrons directed at your little piece of sodium iodide chloride, you also see the interference pattern. So it's a huge breakthrough. It's amazing to see that simple soap bubble experiment that Newton thought about, that other scientists thought about over hundreds of years ago, and finally was interpreted as evidence of wave-like nature of light, turns out to be the basis for establishing the wave-like nature of X-rays, but you use a crystal instead of a soap bubble, and the wave-like natures of electrons. Again, you use a crystal instead of a soap bubble. So this is how the wave properties of matter, like electrons, subatomic particles, was actually established. Okay, I want to work through a problem about the wavelength of a photon, and I think I'm going to do this one on the document camera too. I want to work through, we just talked about X-rays and their wavelength when they're scattered off a crystal. And we just talked about electrons, their wavelength when we're scattered off a crystal. And so I just wanted to work through a problem involving X-rays and involving electrons. So in this problem here, if there's any hope that you can read my writing, I'm asking us to compare the wavelengths of a 10 eV electron and a 10 eV photon. Why am I asking us? So, good question. Why am I asking us to compare the wavelengths of the 10 eV electron and the 10 eV photon? I'm asking us to do that to get some sort of scale of the wavelengths so that we could appreciate the scale of the matter waves of the 10 eV electron and the 10 eV photon, and perhaps we could get some appreciation of how we might see the interference patterns with the 10 eV electron and the 10 eV photon. I mean, could we use a soap bubble to look at the electron interference? Or do we need a crystal to look at the electron interference if it's 10 electron volts? Can we use a soap bubble or a crystal to look at the photon with its 10 NeV? So let's try and find the wavelengths of these two things. There's an important, another reason I'm going to work through this problem. Has to do with the kinematics, what I would call the kinematics equations for the electron and the photon. Both of them exhibit wave-particle duality. That's a common thing about them. But there is a fundamental difference between the 10 eV electron. So this is the electron. We'll work through that. And down here, I'll work through the 10 eV photon. Now, what did I do there? I guess I just made it sort of clearer. The difference is that think about that 10 electron volts. Compare that to the mass of the electron. Compare it to the photon's massless. So 10 eV electron is a non-relativistic particle. 10 eV is small compared to the rest mass of an electron. I'm sure you know this number. That's about 500,000 electron volts. So the kinetic energy of the electron is much, 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 much smaller than the rest energy of the electron, which makes it a non-relativistic electron. So it lives in the world where the energy is kinetic energy, is half mv squared. On the other hand, the photon doesn't even have rest mass, right? It has no rest energy. It just has this energy of 10 electron volts. So it's the opposite. It's relativistic. It's traveling at the speed of light. And so in one sense, we got similar beasts where we're talking about the wave-particle duality of the electron and the photon. In the other sense, from the relativity perspective, they're very different. One's completely non-relativistic, the electron. One's totally relativistic, the photon. And so we're going to use different equations for the kinematics because one's relativistic and one's non-relativistic. This thing is, to calculate the wavelengths, I want to find the momenta of these two particles, and I'm going to use different equations for the relationship between the momentum and the energy of these two particles because one's relativistic and one's non-relativistic. Okay. The energy, kinetic energy, of the electron is 1/2 mv squared. 1/2 is mass times square of its speed. I really want momentum, so I'll write that not in terms of V, but I'll write it in terms of P. It's 1/2 P squared over M. It's the same as 1/2 mv squared. I can use this formula when I want to calculate the wavelength of the electron, the de Broglie wavelength of the electron. That's where I've got to take Planck's constant and divide it by the momentum. I can use this formula upstairs here to rewrite the momentum in the denominator of the de Broglie wavelength equation. I can rewrite that momentum in terms of the known energy, the 10 electron volt energy of the electron. If I rearrange this equation here, multiplying by 2, multiplying by m, taking the square root, I can replace the momentum by the square root of 2 times the mass of the electron times the energy of the electron. And then I can go ahead and plug all the numbers in to this equation. So if I start plugging in the numbers, one thing I'm going to do here, I wanted to do this. I want to use the value of Planck's constant in electron volt seconds rather than joule seconds. I wanted to do that because I've got my, I'm going to use the mass of the electron and the energy of the electron also in units of EVs rather than joules. So the in the denominator here, I've got 2 times the mass of the electron. That's 0.5 times 10 to the 6 EV c squared times the 10 electron volts. That's the kinetic energy of the electron. Sorry, this 6 is completely unreadable, but so let's plug in all the numbers, and as I say, I'm using EVs, not joules, because that's more convenient here. And if you calculate what this number is, I got 0.38 nanometers. And so that's the de Broglie wavelength of that electron. And a key thing there is I use the non-relativistic relationship between the energy of the electron and the momentum of the electron, because I needed the momentum of the electron to calculate the wavelength of the electron via the de Broglie equation. Let's do the same thing for the photon. For the photon, again, I want to use the de Broglie equation. I need I'm going to use the de Broglie equation. I'm going to need the momentum of the electron. The momentum of a photon is related to the energy of the photon by this little equation here. We did meet this once, but we probably didn't remember it. This is the relativistic energy momentum relationship if you have a massless particle like a photon. So this too allows me to use the de Broglie equation for the photon, but rewrite the momentum of the photon in terms of the energy of the photon. The energy will be, the momentum will be the energy divided by the speed of light. And again, if I plug in all these numbers, I'm going to have, let's see, 4.1 times 10 to the minus 15 electron volts. That's Planck's constant, divided by the energy of the electron. That's the energy of the photon. That itself is divided by the speed of light, 3 times 10 to the 8 meters per second. Sorry. And if you calculate that, I got 123 nanometers as the wavelength of the 10 eV photon. So the moral of this story, I guess, look, we thought about a 10 electron volt electron and a 10 electron volt photon. And we calculated the de Broglie wavelength of the electron and the photon using the same equation. Lambda equals Planck's constant divided by P. But although they're both 10 electron volts, the electron and the photon, one was relativistic, one's non-relativistic. That means that they had very different momenta, although they have the same energy. They have very different wavelengths, although they have the same energy. If you look at the two wavelengths, the wavelength for the electron is very short. It's the scale of the distance between layers of a crystal. You would use a crystal to measure this wavelength, to prove that that electron has wave-like properties. On the other hand, the photon has a wavelength that's scale of 100 nanometers. That was more the scale of the thickness of a soap bubble. And so you could use a soap bubble to prove that that photon, or photons of that energy, have wave-like properties. So one would exhibit its wave-like properties in reflection of a soap bubble. The other one would exhibit its wave-like properties in reflection of a crystal because of the very different scale of their wavelengths, although that their energies were exactly the same. What am I doing? I'm going to do a quiz. That's the next thing here. So I'm going to publish the quiz. So here's a question about matter waves and about de Broglie wavelengths. And we're asked to think, oh gosh. Here's a question about matter waves and de Broglie wavelength. We're asked to think about an everyday object, a truck that's moving down a highway, and we're told the speed of the truck, we're told the mass of the truck, and we're asked whether we would observe the matter waves of the truck in our everyday life, or if we can't observe the matter waves of the truck in our everyday life, is it because the matter waves are just too enormous for us to see on everyday distance scales, or is it because the matter waves are far too small for us to see on everyday distance scales? So this is really about calculating for the truck, what is the matter wavelength going to be? We would calculate it with the Broglie equation for the matter waves. It's lambda, the matter wave wavelength, equals the momentum of the particle or the object or the body. That momentum divides Planck's constant. So in this particular case, this is a heavy object, lots of mass, high momentum object because it's got lots of mass. So the momentum is very large, so that when I take Planck's constant and divide it by the momentum that's very large, because the momentum's in the denominator, I'm going to get a wavelength that's very, very, very small. That wavelength is far, far smaller than everyday size scales and is imperceivable, unnoticeable to us. So we never see the matter wave effects of everyday objects like you and I, or trucks or cars or chairs and tables, because they have so much mass, they have so much momentum that the matter wavelengths are so short, they're imperceivable. And so the answer to this one is we don't see the matter waves because the wavelength is way too short. Okay, well, we talked about the idea of matter waves. That was de Broglie. We talked about the proof existence of matter waves. That was Davison and I forgot what the other guy's name is. Got a Nobel Prize, but I've forgotten his name. Anyway, that was the proof by observing matter wave effects from scattering or reflection or diffraction, whatever we're going to call it, of crystals. And the last topic is, what are the implications that matter has both wave-like and particle-like properties? There are important implications, and there's an important equation that kind of embodies, encodes, codifies those equations. So we're going to look at that, and it's called the uncertainty principles. The uncertainty principle is due to another scientist that got a Nobel Prize. It's Werner Heisenberg. And what he realized, what he recognized, so he's the first to realize and recognize this, that the fact that matter has this wave-particle duality, the fact that light has this wave-particle duality, implies that there's a limit on our knowledge of things in the physical world. And also that when we observe nature, when we make measurements of nature, we always alter nature. We always change nature. So these are two ideas. They're sort of a bit philosophical, but they're ideas about the implications, the important implications of the wave-particle nature of matter and light. The point is, I'm making in these next two bullets, this second one and this third one, is how it changed our conception of the universe. So before wave-particle duality, sort of Newton's universe. Newton's universe was kind of, they would call it a clockwork universe. In Newton's universe, if you could know the position and the velocity of every particle in the universe, you can't know it in practice, but if you could know it, you could know it in principle, position of every particle and velocity of every particle in the universe, then you could exactly predict the future. You could exactly determine the future. You would just apply Newton's laws of motion to all those particles, their masses, their positions and their velocities, and you could predict exactly what's going to happen in the future for all of us. It's a completely deterministic universe. You could predict everything. You could predict what you're going to think. So that was a deterministic physics universe where everything in the future was completely predictable by what's happening right now. Wave-particle duality, this third bullet here, says that you can't simultaneously know everything. You can't, in principle, not even in practice, you can't in principle know the position and the velocity of every particle in the universe. Therefore, you can't predict the future of the universe. It's not possible to predict the future of the universe. Therefore, the future of the universe is not a deterministic universe, one that is predictable, rather that it's a probabilistic, undeterministic universe, one that is not predictable, but rather you could just give probabilities for things. So that was a momentous change in sort of visualization of the laws of nature and what they can do and what they can't do, from one in which they could predict everything into the future, at least in principle, to one in which they can't predict anything. They can just tell you probabilities of things in the future. And it's a big change in how we think about ourselves, right? Whether everything's deterministic, and that stupid thing I did yesterday, well, I couldn't do anything about it because it was just determined by my past history, or whether that stupid thing I did yesterday, I could have done something else and it would have been much better. So big change between deterministic and indeterministic universe. As I say, this change from determinism to indeterminism is embodied by, is sort of characterized by what's called Heisenberg uncertainty principle. So I want to introduce Heisenberg uncertainty principle. And I want to show you a few pictures that give you the idea behind why wave-particle duality of nature, light, matter, might lead to this, this indeterminacy, this uncertainty, this inability for complete knowledge of the universe. Here's one picture. I got two pictures here. I'm just going to show this first one. So this is something that we met before. Remember, we met the we met two-slit, multi-slit, one-slit experiment. This is water waves passing through a single slit. There's three pictures of it because there's three widths of slits. On one side, there's a slit that's considerably bigger than the wavelength of the water waves. On the other side, at the right-hand side, there's a slit that's much smaller than the size of the water waves wavelength. And then there's in the center is an intermediate slit. Let's think about it this way. In the slit is kind of measuring or defining the position of the outgoing water waves. So the water waves are streaming from the bottom to the top in each of these pictures. Here's the wide slit, here's the narrow slit, here's the intermediate slit. The slit defines kind of the position of the water waves. This slit defines the positions of the waterways rather loosely because it's a wide slit. This slit over here on the right defines the position of the waterways more tightly because it's a narrow slit. And the one in the middle is somewhere in between. You'll notice something. When you define the position of the waterways tightly like this, well, you kind of get this sort of beam of water waves or stream of water waves that emerge from that slit with that width, but they do spread out a bit. They do start to spread out a bit. When you confine the waterways a lot, over here on the left-hand side, then if you confine them a lot, well, they don't just spread out a little bit, they're spreading out a lot. What you're seeing there in the language of sort of your ability to know the position of the emerging water waves and your ability to know the wavelength of the water waves is that if you confine the position a lot, so this is defining the position very precisely that the water waves emerge from, then you get a big spread in the wavelengths. Now, I don't mean a spread in the size of the wavelengths, but there's also a direction to wavelengths. Look, some waves are going over here to the left, some waves are going over here to the right. We've got a big spread in wavelength. So making the position of the wave well defined with the narrow slit spreads out the wavelengths. On the other hand, if we don't define the position so well, like this is a much wider slit, so I can't say so precisely where in position this stream of waves is. If I don't define it so well, then this problem of the waves spreading out is much less apparent, right? There's a little bit of spreading of the wavelengths over here on the left, a little bit over here on the right, but we've got much more a kind of a stream or a beam of waves traveling this way. So this is a picture showing that for just classical waves, these are just water waves, these are not fancy old matter waves. For classical waves, ordinary water waves, that if you try and define the position of the water wave, you're going to spread out the wavelength. If you loosely define the position of the water waves, then you're going to you can have a better defined wavelength. And that's the two extremes on the left and right. That for waves, it's a characteristic of waves that if you well define the wavelength, you're going to poorly define the position. If you poorly define the wavelength, then you can have a well-defined position. I'll show you another picture or two of that. So in this slide, over here on the left-hand side is little ripples on a pond. And it's not a great picture, but I'm trying to ask you to imagine that these ripples are kind of uniform over the surface of the pond. And they have a well-defined distance between crests, a well-defined distance between troughs. The wavelength is well-defined over here. Look, here's one wavelength, here's the next wavelength, here's the next, here's the next. It's very uniform. So this is a picture of water waves where the wavelength is well-defined. This is a picture, it's given a fancy name, soliton, and you can see this sometimes, but this peak here is also made out of water waves. It's where this kind of wave structure is well defined in position, very well defined in position. I can say exactly where this wave is, but I can't really say what its wavelength is. So over here on the right, this is the left, sorry. Over here on the left, we've got well-defined wavelength, but I can't really say where the wave is. The wave is in the whole pond. I can't point to a location where it is. Over here on the right-hand side, I can say that this wave is right here, right at this position, but I can't tell you what wavelength it is. So this is a second example, illustration, that if you define the wavelength of a wave precisely, that's over here, well-defined wavelength, you don't know its position very well. If you define the position of a wave precisely, you don't know its wavelength very well. So these two things, it's like a seesaw. Imagine a seesaw. Wavelength of the wave is on one end of the seesaw. The location of the wave is on the other end of the seesaw. If I know the location well, I've ruined my knowledge of the wavelength of the wave. That's the right-hand picture. I knew the position well, but I don't know the wavelength. If I know the wavelength well on the seesaw, then I don't know the position very well. That's the left-hand side picture. So these are kind of two extremes. You can't know both simultaneously. And this is really Heisenberg's point, that if water waves, but if matter waves have this characteristic, wave and particle duality, then you can't simultaneously know their wavelength and their position. We can turn this into an equation. This is the equation that describes this effect of the seesaw and whether you can or cannot know the wavelength and the position for ordinary old water waves. So look, over here on the left-hand side, the picture I'm describing, the water waves I'm describing, kind of look like this. The wavelength's well defined, but it's spread out over the pond. We know lambda well, the wavelength. We know the position poorly. They obey this little rule, that the uncertainty in the position times the uncertainty in the wavelength, it's actually the uncertainty 1 over the wavelength, but it's related to the wavelength, is roughly equal to the scale of, think of this as 1, but it's 1 over 4 pi. So this sets the scale of how well you can know these two things. It just makes my argument more about the seesaw more quantitative, right? In this case, we know the wavelength really well. So this term would be small. This is the uncertainty in the wavelength. We know this really well. This is small, which means that this must be big if this product has got to equal 1 over 4 pi. Over here on the right-hand side, this is the reverse. So this is my cartoon of this wave here. It's well localized in position, but it's got a spread in wavelengths. Again, it obeys this same equation. This equation kind of quantifies the seesaw, that in this case the position is well defined, but it must be that the spread in the wavelengths is poorly defined. This delta 1 over lambda is going to be big, such that the product of these two things is going to be 1 over 4 pi. So, you know, we got the seesaw, you can know the wavelength well, but you're going to know the position but poorly. We can know the position well, you're going to know the wavelength poorly. How do we quantify that? It's the uncertainty in the position times the uncertainty in the wavelength. It's the delta x times the delta 1 over lambda equals some number for water waves or classical waves or sound waves or earthquake waves. It's that number's just 1 over 4 pi. This just comes out of understanding of waves and your ability to know simultaneously the wavelength and the, what's the other thing, the position. Well, here's an interesting thing. Supposing I multiply the equation that I just wrote down by Planck's constant. And supposing I think of this picture as not water waves, but electron waves or matter waves, then I'm going to have an equation that says how well you can know the position and the uncertainty in the position, and the uncertainty in what I've written as momentum, because I had 1 over lambda, but I multiplied by Planck's constant. So 1 over lambda becomes Planck's constant over lambda, which is the momentum of the electron matter wave. So just by multiplying the last equation by Planck's constant, it morphs that everyday wave equation result about your ability to know wavelengths and positions into this new principle for quantum matter waves that says how well you can know the position of the matter wave and simultaneously know the momentum of the matter wave. It says that if you know the momentum well, that's this case here, where we know the wavelength well, then you'll know the position poorly. And the product of your uncertainties in the position of momentum will be of order of Planck's constant. Planck's constant divided by 4 pi. If you know the momentum of the wavelength well, that's what's, if you know the position well, that's what this case is, then you're going to know the momentum poorly, such that it is in accord with this relationship here, where the uncertainty in the position and momentum of the particle is order Planck's constant over 4 pi. And so this is the uncertainty principle, and it's just, we just arrived at it by taking our understanding about ordinary waves, water waves, sound waves, other waves, that where we understand that you can't know the wavelength and the position of the wave simultaneously. And then we just applied that to matter waves, electron waves or proton waves, and saw there that you can't know the position and the momentum with both well. If one's certain, the other's uncertain, and so forth. And so that's all that Heisenberg did, was carry over a classical notion about the relationship between wavelength and position for ordinary water sound waves, carried it over to these new unfamiliar electron waves, proton waves, atom waves, and using the de Broglie wavelength showed that you can't know the position and the momentum of a subatomic particle like an electron or proton with both simultaneously. So that's the root of how I started this discussion. I started by saying classically you could find the velocity and the momentum and the position of every particle in the universe. You could predict everything in the future. But Heisenberg's saying with this uncertainty principle, you can't know the position and momentum or position and velocity of every particle in the universe because you've got limited knowledge of it, so you can't predict the future. Here's an analogy of this situation from a Chinese restaurant menu, right? Going to a Chinese restaurant, sometimes there's menus where there's a group of you. Let's just imagine there's me and my spouse. We're going to a Chinese restaurant and we're going to order a meal for 2. And the instructions are that if we're ordering a meal for 2 persons, we've got to pick one from group A and 1 from group B. So we get quite a bit of choice. I can pick from group A and B, but I only can pick 1 from group A and 1 from group B. I can't pick 2. I can't pick 2 from group A or 2 from group B. So shrimp or beef, I can't have both shrimp or beef because shrimp and beef are both in group A. So I can't pick both of those. This is like you can't pick knowing well the momentum of an electron and knowing the position of position of the electron. You can't pick both of those. You can only pick to know one well. You're going to have the other be poorly known. So I could pick to know the position